So I'm Aaron Lasseigne. I have a hard to pronounce last name. It's really not so much hard to pronounce, it's hard to read. And I'm going to do a talk on Ruby and Unicode and what could go wrong. So November 3rd, 2017, which is conveniently 7 months ago to the day, there was a post in the r/Android subreddit. A user had noticed something odd in the Google Play Store. There were two copies of WhatsApp floating around. And so the one on the left, they're downloading it. You can't see it. It's got like 1 billion downloads, right? It's WhatsApp. The one on the right has 1 million, though. It's called Update WhatsApp Messenger. And if we look at a little closer, you can see that they're both from WhatsApp Incorporated. So had WhatsApp released some new thing and not talked about it? What happened here? Well, they opened up the app and it looked like this. This is clearly not their new strategy. Right? Someone had hacked into the system and put up ads, and it's reasonably harmless. But you could imagine if this were, let's say, Chase Bank, and they did an invalid credential log, like they stole your credentials and said, "Oh, sorry, the service is down for the moment. Come back later," and then, later you find out you're losing a bunch of money. So how did this hacker manage to foil Google? Right? This is a company it's an industry giant. They have money. They have talent. It was probably something really, really impressive. Like there was people typing, and I always love this. The two of them on the same keyboard. Like that's how it works. It's just fantastic. Good job, NCIS. So in reality, though, they were foiled by a non-breaking space. That's all they did. They threw a non-breaking space at the end of the name, and it slipped by their checks. So it doesn't take much. Now you might be thinking, we're Ruby developers, we've got strip, we'll just rip that out. But the reality is, strip would not save you in this situation. And part of the reason for that is that fundamentally strings are liars. So they show you one thing, but under the hood they can be something different. And I mean, we're kind of at fault for that. We don't want to know how the sausage is made, we just want to eat, right? We want to see what the thing looks like. We're not concerned with all the underlying details most of the time. And the thing that masks this is encodings. So all the ones and zeros get translated into A's and B's and 5s and 7s and all that with encodings. Most of you have probably heard of this, but I do want to go over a quick few terms just to make sure we're all on the same page with this stuff. So there are coded character sets. Sometimes these are just called character sets. It's essentially just the list of characters with code points associated with them. And a code point is just a unique number. So like A is 1, B is 2, C is 3, however they want to lay it out. A character is anything we decide we need to write, anything we want to write. So obvious things like letters and numbers, punctuation, symbols, so like $. But there's a lot of characters that are hidden that help with formatting and things like that as well. And those are, as far as this is concerned, considered characters. And the glyph is the actual visual representation. So a character is an abstract concept. And then a glyph is the thing that you actually see on the screen. So a character set might look something like this. You can see sometimes things are grouped, sometimes they're not grouped. It's kind of all over the place. If we look at an individual entry, the concept of a lowercase a is represented in this case by the code point 97. We can get this in Ruby by calling .codepoints. It will give us back 97. You can also see the example here of the glyph versus abstract character concept. I'm intimately familiar with A's. So the A on top, the designer decided to go with that kind of hooky over the top thing. And on the bottom, it's more like the O with like a bar slammed into the side of it. But these both represent the same abstract concept of a lowercase a. Most of you, probably all of you, have heard of Ascii, which is the American Standard Code for Information Interchange. It was first published in 1963. It didn't have lowercase letters in it until 1967. So everyone yelled for a few years in there. So you can stop complaining about your grandparents. They don't know any better. And it only used 7 bits. So we all work with 8-bit bytes usually, but Ascii was only 7 bits when it was originally designed. That's because it was designed to work on machines like this. This is a teletype Model 33. It's essentially a keyboard, a printer, and a modem slammed together. And it would let you type messages, send them to other teletype machines or other groups of machines, so you can think like Slack back in the day. Right? And it meant that Ascii included a lot of control codes to be able to handle that transmission side. So this is where you get things like tabular data, tabs, right? It meant that the printer could know where to line them up. There's vertical tabs, which we don't use much anymore, although these days tabs are mostly just an argument about editor space anyway. So Ascii included a lot of interesting control codes. This is the inside of one of those machines, and I pointed out because there's a piece of this that I love. If you've ever been in your terminal and you've like backspaced too far or tabbed without a completion or heard something and heard a ding, or you've seen your screen flash, the visual bell, right? There's literally a bell in this machine. So you could send a bell signal and ring it on the other side. So as computers grew and evolved, we kind of moved into doing 8-bit bytes. That was a debate for a little while, and people settled on 8. Because why not? I don't know what the actual reason is. But Ascii needed to move up. So, oops, backwards. So they took the Ascii and they tacked a 0 on the front. And that's great, everything's compatible. But this also opened up a world of additional characters, right? Because we can flip that to a 1 at the front instead of a 0. And we get a whole another 128 characters. And this is a little known fact, but it turns out there are many languages in the world, and not just English. And these other people were like, hey, can we use computers too? Because that'd be great. And actually write with our language. And so they took this, they flipped the 1, and they started throwing characters in there. And individual languages, or sometimes groups of languages if they use shared characters, could have their own encodings. And this led to this kind of explosion of extended ASCIIs. So you've got ASCII, and then ISO 8859-1, which if you've been doing this a while, you might recognize. It's also known as Latin 1, if that sounds more familiar. So that's great, and ISO people were like, this is awesome. We're going to make a bunch more. We're going to skip 12, because that's a crap number. I don't know why they did that. So then Windows came along, and Microsoft, in their fantastic wisdom, they're like, we're going to make something that's super close, but we're going to add smart quotes and make it just different enough that it breaks across everything. And for a long time, software had to actually try to guess, because people would put the wrong encoding, and so they would try to fix it for you. And then they're like, let's do this a bunch of other times. TIS came out. This is the Thai industrial standard. So they're like, hey, we need this. We'll do it. ISO was like, no, we're going to steal it. So the ISO 8859-11 is an exact copy, but just to spice things up, they added one more character, which, by the way, was a non-breaking space. There's the KOI 8 series, which is like Russian type of languages, and this is the mid-'80s, and ISO's like, hey, this looks interesting. People are like, you're not going to mess with Russia in the mid-'80s, and they're like, hold my beer, because we're doing it. So they made ISO IR 111, which is an exact copy. So now we got that fun. And this is just a small snapshot. There's a lot more. Things went bad fast. So what you would end up with is you've got ISO 8859-1 smorgas. You send that to someone with a Mac. It attempts to use Mac OS Roman. All the ASCIIs line up because they're all supersets of ASCII. Those parts work. But the other characters are different. And you end up with this. This is called mojibaki. It's a Japanese word meaning character transformation or character changing. And it's when you have an encoding that goes awry. So mojibaki. It's not the same, by the way. If you see those little white boxes on the screen, that means there's no glyph to represent that character. That's usually called tofu. So don't mix them up. So the point is this sucked, right? We had tons of encodings. We had some that were competing for the same space. They weren't composable. So if you were wanting to write a paper in French on the Russian language, good luck. Wasn't going to happen. So along comes Unicode, which is the universal coded character set, right? Their design was basically a superset of the ISO 8859-1 because that was super popular, which also makes it, by extension, a superset of ASCII. So it was really backwards compatible, and their design was to handle anything we could need written. So it's not just languages, but it's also math symbols, music symbols, emoji. The only thing they won't put in there is made-up stuff. So no matter how many times you try, you will not get Klingon, Dothraki, Elvish. None of these will appear. And apparently people have tried. So it's run by the Unicode Consortium. They're the group that keeps all this stuff going. They've got a group of members. It's a pay-to-play system. So you pay to be on the board. You'll recognize a lot of the companies up here, I suspect, including Google. So they're intimately familiar with this, which just shows this happens to the best of us, I guess. The current Unicode version is 10. The first was released in 1999. They iterate about yearly at this point. And the encoding, the Unicode character set is different from the actual encodings that you've probably heard of. The encodings are an implementation of that character set. Three of the most common are UTF-8, 16, and 32. The UTF stands for your Unicode transition format. The number behind it is the code unit size. So it's the number of bits needed to represent one character, the minimum number of bits needed to represent one character. It's also the minimum step size. So if you need more bits, you have to increment by at least that much. So minimum size on UTF-8 is 8 bits. This makes it Ascii compatible. You can switch the encoding, change nothing with the bytes. Keep them all the same, and it'll read just fine. But you can also go up to 4 bits, or 4 code units, to represent the whole of the whole of Unicode. UTF-16 uses 16-bit steps, so the first one's going to be 16. If you need more, you have to add another 16. And 32 is a fixed size encoding. And they did this so that you could have a variety of options available to you. UTF-8 is almost always the most space-saving of the group. There are a few times where UTF-16 is actually slightly smaller. Generally, UTF-8 will save more space on disk transmission. It's backwards compatible. But if you need to index into some distant part of a string, you have to walk the string and check because all these characters are variable. UTF-32, you can do the math and then just jump right to where you need to be because they're all a fixed length. And then UTF-16 is just terrible. It's the worst of both. When you use UTF-16 or 32, you're using multiple bytes for that code unit. So you start running into problems with the byte ordering. So in some systems, they order most significant byte to least significant byte, which is kind of what you're probably used to seeing, and that's big endian encoding. And then flipping that, you get little endian encoding, which is the least significant byte, to the most significant byte. So for systems to be able to be compatible, they have a BOM, which is a byte order mark, and it basically says what order those are in, so that a system can look at it and say, okay, you send it to me in big endian, I read things little endian, I'll go ahead and flip everything so I know that I'm doing this correctly. We can see this because if we do A encode UTF-16 encoding, it tells us it's a dummy encoding. So basically, it's saying, I'm doing this, but under the hood, it's really one of the other two. I thought dummy was not very Minneswan, though, like fake encoding, or I don't know. So there are also UTF-16 BE and LE for big endian and little endian. So the byte layout for big endian is, remember earlier the A was a 97, so they just slapped a 0 opening byte, done. The other direction flips the 2. So what happens if we just say UTF-16? We actually get 4, and it's because we get that BOM attached to the front, that byte order mark that tells it which way to go. This also applies to UTF-32. Now, most of you will work in UTF-8. It's the most popular, space-saving, backwards compatible, all those good things. It was originally presented in '93 by Ken Thompson and Rob Pike. These names might sound familiar. Most recently, the two of them, along with another gentleman, did the Go programming language. So that might be where you've heard of them from. They've done a lot of good stuff. In the early 2000s, you can see the red line on here is Ascii, and this is a web page by encoding. So Ascii is the dominant force, but obviously it's not for everybody. UTF-8 is the blue line skyrocketing up past it, and this ends in 2012. I don't know what today's numbers are. I'm guessing it's probably even higher than this at this point. But they crossed paths in 2008. That was when UTF took over as the major encoding on the web. It's also about the time Ruby introduced it as the default encoding. This was the 1.8 to 1.9 switch. We went from Ascii to UTF-8 as the default encoding. So that means Ruby has Unicode support, right? Maybe? So let's take my name, and I'm going to put I'm going to put a little umlaut at the front. And if we capitalize this in 1.9, even though UTF-8 is the default, nothing happens. It wasn't actually until Ruby 2.4 that this got fixed. So pretty recently, really, in the scheme of things. They also did this with capitalize, upcase, downcase, swap case, all the kind of things related to upcasing and downcasing things. Upcase is an interesting situation because it's actually contextual. Most of the people in this room would uppercase an I into a capital I like this. But if you were using a Turkic language, it actually upcases it into, it's a capital I, but there's still that dot on top. So there's things that will never be able to handle for you by default. Sometimes you just have to understand the context of what you're working with. And in addition to Turkic, you can pass Ascii, which gives you the old behavior, or Lithuanian, which doesn't do anything, but hopefully someday will. That's what they say. I don't know why they just didn't leave it out. But this is another character. This is a German sharp S. Upcasing this produces two capital S's. This is actually correct. It's a legitimate replacement. Two S's is considered the same. We can downcase that. If anybody's not familiar, the underscore is like previous value. We get two lowercase s's. If we just call downcase on the sharp S, though, it's going to stay the same. It's not going to downcase it. You can see where this might lead to some comparison issues. Unicode, aware of this, has what's called case folding. So you can pass fold to this downcase, and it will actually convert it to this double S setup. And there's a number of other characters that this works with. And it's important because this happens when you do case compare. So these will case compare to true, even though they are different, because it uses that case folding. However, the non-predicate version, note the lack of the question mark, is Ascii only. This would be a 0 if they were equal. So this is a fun little watch out. Now, I've been talking about some of this stuff, but whitespace was what originally got this thing going. So let's talk about some whitespace for a minute. Most of us are probably used to thinking of whitespace in terms of space, new line, tab, ASCII things. So here's a picture of all the ASCII whitespace. It's a little bit of it. Here's all the whitespace in Unicode. You can see there's a lot more here. No, these are the actual, I'm not even sure I have a full list if I'm being honest. But this is a massive list of white space that you can use in Unicode. They have a lot of things in here. You see like EN, quad, and line separator stuff, Braille space, right? So you could sub that in for a normal space and trick people with that, and it will be reported as a different character as far as Ruby's concerned. So back to our strip thing though. Let's run strip, right? Well, strip only handles the ASCII side. It doesn't do any of the rest of this. There's been an open ticket for 2 years. They haven't resolved it yet. So I don't know why or what's going to make that happen, but for now, you're on your own. There's also a whole list of invisible characters, right? So those are fun. You can jam those in all kinds of places. And you can imagine even if we remove some of these, it's really hard to pick some of these things out. Strip wouldn't be enough. You'd have to pull them out of the middle because like the hair width space is, you know, like the width of a hair. So you can put that in a lot of places and not have it be noticeable. Yes, there's our non-breaking space, by the way, that did not get caught in the strip. So ideally, we could do something like use TR, maybe get a list of white spaces into some constant and pass them through strip ML turn them all into regular spaces we're comfortable with, squeeze them down. Maybe we've helped things out a little bit, made it less likely to have this happen. But we still have those invisible characters I mentioned. And I want to kind of go on a tangent for a second, tell this fun story I found about invisible characters. So there's this guy, Tom, and he's part of a group of gamers. They play a variety of games together, and they have a private forum they use to communicate with each other and talk about, like, you messed that up, whatever, we should have done this. Well, somebody was posting this stuff externally, and Tom got pissed. He's like, I want to figure out who this is. So he makes this plan. He says, I'm going to take the username. We're going to say jerkface. I'm going to convert it to binary, and then I'm going to use 0 width space as a 1, and a 0 width non-joiner as a 0, and I'm going to insert it into every single string the forum outputs. So they went and found a copied version, ran this process backwards, and figured out who the user was, and then permanently banned them. So I think there's 2 lessons from this. 1, it's hard to know what you're copying because these characters can be inserted anywhere. And 2, just don't mess with Tom. Like, this is over some video game stuff. That's what I took away from it. So maybe we can do something similar here. We can delete the invisibles, maybe keep them in a constant, make sure we change it up with anything that we find along the way, because, like I said, it's hard to get all these pinned down. So white space is maybe fixed up, invisibles are gone. We still kind of have some issues, though. E-length is 1 or 2. Both these are legit. It depends on how we represent the character. So there is a single character, lowercase e, with an acute accent. But you can also represent this as lowercase e followed by an acute accent diacritical combining mark. It will display, no matter which one of these you use, as the one on the left. They look identical, you can't tell them apart. Ruby, however, will report them as two characters. The one on the right, that is. So if you do something like this, right, I just kind of like jammed a bunch of them on there. And it kind of worked out. I got like two smiley faces in there just totally by accident. So if this were part of a real language, you would look at this and you'd say this is one character, crazy character, but one character. Ruby will tell you it's 21 characters long because each of the marks gets counted along the way. We can kind of help this with graphemes. So this is basically the idea of what a human would view as a single character is what we want the computer to tell us as a single character. So it's a way to kind of handle some of this stuff. And I'm going to go through a little bit of examples of this, but we're going to do something a little more fun and use emoji to do it. And to do this, I'm going to need a zero width joiner, which looks like this, zero width. So we're going to take some emoji. By the way, this works in your terminal. So here we have a little family. We've got a dad, a mom, a kid, a daughter. Dad's got a kind of rockin' stash. I don't know if you can tell. It's blonde, so it fits right in. But he's got like a nice 70s cop stash thing going on. And we can zero join them together and produce this picture, right? This new emoji. And there's an individual code for this, but you can construct it out of the top three. Also, you might, again, it might be hard to see, but Dad had to lose the stash for the family photo. It's gone. It just vanished. So, all right, we decide we want to add a kid to the picture, a son. He's the same age, so they adopted. They adopted. They're good people. So we do that, and it will produce the new one. And we have the new family with the definitely not kidnapped adopted son. We can also do things like sub these people out, because these are still individual characters at this point. Right? We have the representation. You can find the one that is the group and have that be that one character, but it could also be this group of characters. So we can do this, and we can end up with two dads and a daughter and a son. And by the way, one stash, one no stash, if we're keeping count. There's also some other things this works on. So when they first did all these human action things, it must have only been men because they forgot half the population was women, and they made them all men. So you can use a female sign and get a female runner. We now have these actually in there, but this is a step to get to that. There are also regional indicators. So you can use a U and an S and get the American flag. And then you can also do things like join, the thumbs up and all this kind of stuff we love with skin tones, so that you can have a variety of skin tones. Now, on my computer, this actually did not work. So it's not quite up to date yet, apparently. It should look more like that. So we can get these grouped up with graphemes, whether we use the individual or the sort of zero width joined group. They can be treated as a single unit. So back to the E example for a second. Grapheme clusters length 1, it will be 1 no matter which type of E this is, the single character or the combo. This just showed up though in 2.5, like literally December. So this is, still pretty new to the game. Prior to this, you would have had to use /x in regex. So regex, interestingly, has had this for a long time. The engine was available to be able to pull graphemes out. They also added each grapheme cluster if you want to be able to walk through in each kind of way. And it's worth noting that the original design was Ascii, and you can still see it in a lot of Ruby code. So if you use rjust, this lets you justify text. So for example, if we have the E that's the single character, rjust3 puts 2 spaces and then uses the third space to drop that E in. But if we do the E that's the 2 character type, we get 1 space, and then what looks like the 1 character, but as far as Ruby's concerned, it's still using 2 slots. So there's a lot of cases where this can go a little sideways. right? Our accent, one of them's above the quote, the other one's now over the S. This is not good. So we can now use grapheme clusters, reverse join, and have what you would expect to get, regardless of which kind of E is in your stuff. So that's fun. The problem is these still don't compare right. So we've grouped them up, but they're just tiny strings that are now messing with us. Let's take a look at company names again. So I made up this, I hope I made this up, Antec, and they have an A with a ring above it. But not all A's with ring above them are A's with rings above them. So the one on the left is a capital A with a ring over the top, used in like Swedish and Danish. The one on the right is the symbol for the unit angstrom, which is a 1/10,000,000th of a meter. So these are separate code points. They are separate abstract character concepts. One of them is an A in a language, the other is a unit symbol. But they use the same glyph. They are visually identical. You can't tell them apart. So if we're trying to fix this, and we're at a Google level and we have international people, this could be an issue. There's also ligatures. So these are typographical flourishes. So you can see the first one has none. The second one, the second F and the I have kind of combined. The F is like reaching over to dot the I. And then the third one, there's a line straight through the F's and into the I. And all three of these will report back as being different. So you can see again where we might get confusing things that people wouldn't notice, potentially, right? They also report back because they are individual characters in Unicode. They're not combinations. They report back as individual characters. So O, FFI ligature, C, E. And they are not equivalent if you look at them in text. Not surprising at this point. So we're screwed. There's nothing you can do. Thank you for coming. That's the end of my talk. No. Unicode understands that this happens, and they provide Unicode Normalization. So they provide this concept, and they tell people how to implement this Unicode Normalization. Ruby added this in 2.2 with the aptly named Unicode Normalize. There are 4 types of transformations that come in this that allow you to normalize your text, and they're broken into sort of 2 major categories, Canonical Equivalence and Compatibility Equivalence. So canonical equivalence means that you have equivalence between characters or sequences of characters that are the same abstract character and have the same parents. So if we look back to the E we've been looking at, an E with an accent and an E with a combining accent would fall into canonically equivalent. They are conceptually the same character, and they are visually the same character. So we have the normalization form canonical decomposition. This is the process of taking a string and ripping them apart. So you see like the C that has a little tail, the sedalia, rip it into 2 pieces. It will also reorder marks, so for making comparisons more, allowing you to compare things. Obviously, if the dots were reversed, you'd get different strings, even though they should be the same thing. So it will mess with the order of the marks to put them in a prescribed order. Some Asian languages also have combining marks that will get split apart. And then there's also singleton equivalents. So singleton characters are characters like that A with the ring and angstrom we were looking at earlier, the characters that are identical. The example here is the Greek omega and ohm. So they will always be reduced to one of those characters. So it will always become the Greek omega. So if you've got physics stuff, you will lose the meaning of ohm as far as the character is concerned. Visually, it'll all look good, but it is not a perfect system in keeping meaning of what you're working with. So if we've got that C with the code points, we can call Unicode Normalize NFD, which is the normal form decomposition we were just looking at. We can look at the code points, and it's now capital C, followed by that diacritic. This lets you do some fun things. The combining marks are in a range. So we can take words like resume and Englishize them by ripping out the combining marks. So more to the point really is if you're doing sorting or searching or things like that, ripping out these characters might make your search more accurate as long as you're doing it with the search content as well. And of course, for anything you're going to do, always keep a copy of the original, because it's easy to screw up, and it's best to always have what you started with. Normal form canonical composition, it's the other way, kind of. So it actually rips everything apart first, no matter what it's looking at. It rips everything apart first, and then it slams everything back together. So you still get all that reordering. You still lose the meaning of things like ohm. But it will put, oops, oh no, there we go. It will put that character back together. These transformations are, as I kind of mentioned, they're not really reversible, which is why you should keep originals. They are idempotent. You can just run them again and again and again and again, and nothing will change. The second form is compatibility equivalence. So this is NFKD, normal form compatibility decomposition. So this is where you get characters like these script characters you might have seen people use in their Twitter handles and things like that. They're math characters. You can reduce these back to their original A, right? 1/2, this is, they actually call them vulgar fractions, apparently from the vulgar term common, not because they're vulgar in the sense that we think. And those will get converted into, this one's an interesting one. It's not 1/2, it's 1 fraction/2. So you still have kind of a different slash character than you might expect. And the nice thing is you can take ligatures and you can reduce those as well. So this is a way to really break it down to its most base components. You can have problems though. 3 to the power of 2 will become 32. I think you can imagine where this could go wrong, right? Moon landings and such. So it's helpful, but it isn't always perfect. So the two forms are the NFD, the canonical decomposition, and the compatibility decomposition. And the canonical is really strict. It doesn't change too many things. Compatibility, you saw, is much more lenient. It's much more liberal. I kind of try to remember it because K for compatibility is pretty liberal. Kind of like using it for, say, conference, right? Cool, RubyHACK, you're in good company here with Unicode. The NFKC uses that compatibility mode decomposition to break everything down, and then really is just the same like recombining that you got before. It's not going to put ligatures back together. It doesn't know that it was a ligature to begin with. You're not going to get any of that back. It's not going to go back to being a fancy A. It has no concept of this. It's just kind of gone to the wind. So we could normalize the string with NFKC. We could fix up the white space. We could clear out invisibles, and we're on, at the very least, a much better path. I don't want anyone going into their work and being like, if we do this, we're secure, and Aaron said so. That may not be the case. Talk to Jeremy about security, not me. But we're definitely better off than we were, and we're certainly not going to get tricked by a non-breaking space. So does Ruby have Unicode support? Kind of. I mean, they're still working on things. Like I said, the Lithuanian's not there yet. Strip doesn't remove all white space. You could say that that maybe is something that should happen before we say it's fully Unicode compliant. But things have gotten a lot better, especially over the recent years. There's been a lot of improvements. It seems like it's continuing to go that way. So I think it won't be too much longer before we can be pretty confident that it will handle most everything that Unicode prescribes and wants us to be able to handle. So once again, I'm Aaron Lasseigne. You can find me on pretty much all the places as Aaron Lasseigne, if you can spell my name. I have a book, Mastering Ruby Strings and Encodings. So if you thought this was interesting and you want to like nerd out on the more deep kind of pieces of this, you can go pick that up. I have 20% off if you use RubyHACK. And you can find that and me at aaronlasseigne.com. And thank you.